Hi, Zaya.
Hey,
Can,
Professor, good.
hey, can you hear me?
Yeah, I can hear you good.
Great. I'm glad to see you tonight.
Good to see you too. Good to see you. I know how to come back to the office hours.
Yeah, right? We can get a lot done in office hours.
Yeah, I know. Let me get my. I'm just now getting back in the house, so let me get my stuff
Yeah,
ready.
yeah, that's fine. I'm a little behind the curve here tonight myself. I was just finishing up grading. So I am ready when you are, but you can take a few minutes to collect yourself if you need to.
Almost ready. I think. I don't really feel like there's like a specific thing.
Well, you
Uh,
know what? If you have a topic,
we
like just a
can.
general topic you want to talk about, we can do that.
All right. Let me go through the notes. Actually, let me go through my last special homework. I'll be right back. I'm gonna get it out my
Hey,
bag.
that's a great idea.
Actually,
I'll get them too in front of me.
get them from me. Special homework we do. Number five. This divisibility again.
Yeah, I got four, five, and six here. We can look at any, or we can even look at three and two if you need to. But I've got them all sitting here in front of me.
We can look at four.
Oh yeah, four with the circuits.
Four.
Four was
Oh,
circuits. Five was the first really big proof one, and six was two proofs plus the stuff about prime factorization. And then there's seven coming up.
yeah, there is seven coming up.
We can talk about seven if you want.
I say let's go through because we did a little bit of six last office hours. So
We
I'll
did.
say five. What are we talking about? Just a part number P.
Yeah, you want to talk about five?
Yeah, let's talk about five. Let's talk about five. Let's talk about
All
five.
right, so the first question on special homework number five, basically five is just to kind of walk you through the difference between, here we'll write a few notes, the differences and similarities, and there aren't that many similarities, between proving, well, an existential statement versus a universal statement. Let's just make sure we understand that these two kinds of statements are proven very, very differently, right?
Mm-hmm.
With an existential statement, let's say the form looks like this. There exists an X, maybe there exists a Y, such that something happens, something is true, some predicate, P of X, Y, as opposed to for all X and for all Y, something is true. In other
Mm-hmm.
words, if X and Y are in, their domains, whatever their domains are, then P of X, Y happens.
Mm-hmm.
And a lot of times we write this as an if then, if something is true for X and Y, then some conclusion happens. Okay. So the big difference is we can use an example for an existential statement. Here we can use an example, but if it's universal, we cannot use an example. Over
So,
here, we find our example, right? Because we do scrap work, right?
yep.
And then we write it up. We consider, X equal and Y equal, and then one, we have to verify X and Y are in the correct domain sets. And then two, we verify the property holds, you know, P of X, Y. Here, if it's a universal statement, we can't use an example. We must use variables, the definitions, algebra, and finally, things we may assume without proof. Remember, we have those two things we can assume without proof. The closure properties, things we may assume.
As you may assume without proof.
Yeah,
Like, for
yeah,
example,
without proof. Like sums of integers or
yeah,
integers
products of integers, products of integers,
or integers.
are
What
integers,
else? What other kind? Differences. So
differences of integers,
sums, differences.
and products of integers are always going to be integers.
Yes, perfect. And products of integers are integers. So we can use that. And what's the other thing that we can use without proof? What do we call it? Remember what we call the other one? The ZPP
The zero product, I forgot what it's called.
property. Mm,
Zero product property. Yep.
good job. Zero product property. And that says, if X is not zero and Y is not zero, if we have that,
hmm
then the product XY is not equal to zero. And this applies even if we've got lots of factors, like an A and a B squared or whatever.
hmm
And then we have to show, oh, wait, wait out. We assume the hypothesis. So that's, the P of X, Y. That's our hypothesis. And what do
Yeah.
we wish?
You wish to show then Q, X, Y.
Yeah, exactly. And then we prove the conclusion follows. So that's the basic kind of, you know, real essential stuff going on that makes these very different kinds of proof methods. All right. All right. So that's a good page one. So let's take a look at some of those problems or some similar problems. Here, shall I just make some up and we can just
We
go
can
through
consider-
some?
Yeah.
All right. Do you want to do an existential proof first, or do you want to do a universal proof first?
We could start with the existential. I remember the existential being a lot easier because we were able to just plug in numbers and kind of play with it.
That's
But
right.
yeah,
So,
we could do existential proof one.
let's say we're asked to prove the following claim. It's going to be a true claim. I would not ask you to prove something that isn't true. Okay, let me just think up something here. There exist prime numbers P and Q such that, let's say, 2 to the P minus Q is composite. All right.
Our numbers P and Q such that 2 to the P minus Q is all right, cool.
So it's existential, right?
Yeah.
Let's do some scrap work.
Mhm.
Now, did anything in this particular statement indicate that P and Q have to be different from one another?
Nope.
Right.
So they're just prime numbers P and Q such that 2 to the P is composite. So they could both be prime numbers. So what we can start with what 2 and 2.
So let's try a couple. All right, what do you want to try first?
We can start with 2 and 2.
Yeah. Then notice P equal Q is okay. All right, so P equals 2 and Q equals 2. Let's try it. They're definitely both going to be prime. We'll be able to easily say, hey, they're only positive divisors or 1 and 2. So they're, it's prime. So 2 to the P minus Q is 2 squared minus 2. What does that turn out to be?
Or I mean, excuse me, 2. 4 minus 2 equals 2.
Yeah, and it's not
Like
composite, so it's not going to work. Okay, now what?
2 second. Sure. I'm following in my head, but not on my, not on my. It's like head math, kind of.
I know, right, right.
So
But
I end up.
you got to write it out. Yeah. Do you want to try
So we could do.
two
We
and
could do.
three or
Yeah, we
three
could
and
do.
two or
I say let's do 3 and 2.
P equals three? Yeah, because we're going to be subtracting Q. So we need two to the P to be big enough.
Yeah.
Q equals three. Okay, they're definitely both prime. So two to the P minus Q is two cubed minus two. That'll be eight minus two. That's six. What do you think?
6. We found our answer.
Yeah, we found one. It's definitely going to work. Now let's write it up. Okay. So here's our proof. Since it's an existential proof and we've already considered it by doing scrap work, let's just tell our reader, hey, consider this, consider P.
P
Oh, did
equals.
I say P equal three and Q equal
No, yeah,
three? I
sorry.
meant to
Q
put
equals
two
2.
here.
Of course, you're good.
Yeah, let's get that right. So consider P equal three
3 and
and Q equal two.
2
So let's do the first thing. We got to verify that they live in the right domain set. So what do they have to be?
integers.
They are, but look at what
Oh yeah,
kind
prime numbers. Yeah.
prime. So notice P equal 3 is prime, and we'll say exactly why. Because it's only divisors, well, it's only positive divisors
Positive desires are itself and 1.
and 1. Also, we got to say Q is prime. Q equal 2 is prime. Same reason, right?
Yeah.
And you could even say this all in one fell swoop if you wanted to.
Okay. Notice P equals 3 and Q equals 3. I mean equals 2 is prime because it's only positive divisors are itself in 1.
Yeah, we'd say R prime. If we're going to do them together, it's
Yeah.
plural. So we say they
Plural.
are prime because their only positive divisors are themselves and one.
Yeah.
See what I mean? So
Yeah.
you want to kind of make the English work.
Yeah. Oh.
All right, now we're going to verify the property, which is this. Now, let's look at, we just basically write our scrap work down. 2 to the P and tell your reader what you're substituting into, right? So it's 2 cubed minus 2, which is 8 minus 2 equals 6. Now, how are we going to show that 6 is composite?
We have to show or we have to display by the definition of composite. Well, like what 6? So we have to show that 6 is divisible by more than just itself in 1.
So let's give a factorization. How can we factor it into a product of an A times a B?
How do we factor 6? We could factor by using what 2?
Yeah, 2 and what's the other factor?
With 3. Yeah.
3. And 2 and 3 are integers, and they're both bigger than 1.
1.
And that's it. So it is definitely easier than proving a universal statement. But there is work to be done. We have to be careful to get full credit. We have to, discuss, this stuff.
No, this makes sense. And what? Yeah, they're both graded in. Yeah. Okay. All right.
All right.
Yeah, I'm good on this. I just
Mhm.
wanted to refresh, but I remember this. I remember this.
All right. Now let's do a universal one. Let me think of a good universal statement. How about we use the definition of divides? That's a good universal. For all proof, for all integers A, B, and C, with B not equal to 0, if B divides A and B divides C, then B cubed divides A cubed plus A squared C. How about that?
You so
So how should we start our proof? I,
start off
mhm. I went
by
ahead and said B is not 0. So I went ahead and said, hey, I'm going to include that as part of the hypothesis.
yeah. So yeah, assume that B does not equal 0.
First, let's say what A, B, and C are, and then B is not
Okay,
equal
yeah.
to 0. What
Right.
else should we assume?
B divides A and B divides C.
Great. What do we wish to show?
B cubed divides A through A cubed plus A squared C.
All right. So we'll dig into that in a minute. Let's by the definition of divides, what kind of equations do we get?
So hold on, let me write.
Okay, so B divides A. What
B.
does that mean? It means something.
It means A equals B times an integer. We can use a variable. Okay, yeah.
Okay. Yep. Where K is an integer. And the other piece of our hypothesis happens to be that B divides C. And what does that mean?
C equals B times an integer. We use, oh, you want to use A
H. I'll
or
use
A.
H. Yeah. Why not? We could use J, but I'm going to use H. All right, so let's dig into our wish just a little bit more so that we know what we're really shooting for. What does it mean to say that B cubed divides A cubed plus A squared C? Like, what do we really need to show?
Um, I mean, we could just kind of go A3, I mean, A cubed, excuse me, plus A squared C equals B cubed times
Good.
an integer. We use M.
Very nice. Very good. You caught the fact that it's B cubed that needs to be the factor that we pull out. All
Yep.
right. So we're shooting for this. So we've got, this in our hand. We're going to use this. We're going to use this. We're going to use this. And we're going to use this. And I'm even going to put my little dreamy wish cloud around my wish so I don't get confused. This is a wish. And we also wish to prove that. Okay. All right. So let's start attacking a cubed plus a squared c, because that's really the quantity that we need to look at. Like when we write it just like this, it looks like we need to look at b cubed, but what we really need to look at is a cubed plus a squared c. All right, now let's look at a cubed plus a squared c. What
Say that again.
Let's look at this expression, a cubed plus a squared c, right? Because
Yeah.
we need to say something smart about that. We need to show it looks like this. So what should we do to get closer to this from a cubed plus a squared c?
Say it one more time.
All right. So we want to transform a cubed plus a squared c into something that looks like b cubed as one factor times something that's going to turn out to be an integer. We're calling it m here, but it'll be something a little more complicated than a single letter.
Uh-huh.
So we got to look at a cubed plus a squared c. We've
Uh-huh.
got all this proof money. So
You do.
to get this part of our wish, which is part one of the definition of divides, we'll use part one of the definition of divides here and here.
Uh-huh.
When we're trying to get part two of the definition of divides, prove that this m, whatever it turns out to be, is an integer, we'll use the part two.
We got to use part two.
We'll do
So,
that later. But right now, let's just try to get a b cubed times an m. So let's start using our proof money. Let's start spending that. What
so
can
a, oh yeah, so it could be uh a by substitution.
yes,
We could use bk cubed. Yeah, okay, yeah, that's good. And
right,
then
the whole thing, yeah.
yep, and then we could do plus bk squared times bh.
Nice. And now we do a little algebra. We use our laws of exponents, right? If
Yep,
we have x, y to a power k, we can distribute that power across the factors. It's x to the k, y to the k, right?
yep.
So how can we rewrite bk quantity cubed?
Wouldn't you be able to just do what b cubed k cubed
Yes. And
plus
now,
b squared k squared plus, or no, excuse me, times, and then bh because there's no exponent.
great. And then there's another rule that says, hey, if you've got x to the k times x to the m, what do we do with those exponents?
You add the exponents together or you
You
put them
add
together.
them.
Yeah.
So we can rewrite the second term and put the b's next to each other, right?
Yep.
So now we've got these b's kind of gathered together. And what is b squared times b? So that's really a b to the 1, isn't it?
Yeah.
So what is that really?
I want to say a b cube
Uh-huh. And then we have k squared h. And that k squared h is going to turn out to be our integer
um,
m. So we'll have to talk about that in a minute and explain why it's an integer. But right now, we've got part one of the definition of divides done. See, this is part one. We used the part ones to get the part
the part
one.
two. Yeah. So we use part one to get the definition of divides and actually write it out to explain what like these integers mean. Well, by substituting, by using our substitution.
Yeah, we burnt this and we burnt this. We spent them here
Uh-huh.
and here. And now we're going to use the fact that k is an integer and h is an integer to start explaining why our m, which is k squared h, is an integer.
The integer for sure.
So we talk about this. We say, hey, Since k is an integer and h is an integer, and what do we have to say about the integers? What's
Uh,
the how are
because
we building m
we could say because products of products are integers.
of integers
Excuse me, products of integers are integers.
are integers? And now we go ahead and tell our reader what our m is. M, which is our k squared h, is an integer. So now we've got that part two of the definition of divides done. So we have now just shown that we've got a cubed plus a squared c. Oh, wait a minute. I missed a step. This is premature. We have to put, oh, what am I thinking? I guess that's why I left a line here. We need to pull a b cubed out of both of these before we do this. This isn't our m.
So we have to pull a b cubed out of our B3.
Uh-huh, out of our b cubed k cubed. And we're going to pull a b cubed out of this because these are being multiplied. So it's b cubed times, well, what's left when we pull the b cubed out of b cubed k cubed?
What's left when we're taking B cubed
Out of
out of
both of
B.
these. I forgot to do that step.
So basically, are we
Yeah,
basically
we're factoring out the
okay?
b cubed. So when we factor b cubed out of b cubed times k cubed, what's left?
Okay,
Cubed, good. And over here, when we factor the b cubed out of this big product, what's left? See,
my factors are
well,
better.
we're factoring out the b cubed from this
B
whole
cubed from
thing.
this whole thing.
Uh-huh. So when we pull out the b cubed, when we pull this part out front, what's left?
It's gonna be B. Is it gonna be B squared?
K squared h. See, we can check it. If you to check that we factored out the b cubed properly, we can multiply b cubed back across this parentheses to see if we did it right.
Oh yeah, and you're right.
See what I
And
mean?
yeah, so if you were to just add back in B or not technically multiply it,
It's
you
called
would get
distributing,
you'd
yeah.
be yeah distributed probably like you'd get
B
B3
cubed,
uh
K3.
K3 plus B3 times
K squared.
K2H exactly. So you basically just removed out the B3.
Yeah. So now this is our M. I don't know what I was thinking. This whole thing is now our M. So it's since K is in H and K is in Z and H is in Z and products and sums
And some
of
integers
ints
are gonna be integers.
are ints. M equals K cubed plus K squared H is an integer.
Uh-huh.
I left out half of it before. So that's what we need. So in fact, a cubed plus a squared c turns out to equal b cubed times an m, which is this, and we said it
Uh-huh.
was that. Where what did we find out about m?
That M is an integer.
It's
Uh,
an integer,
it's an integer.
and that's exactly which means exactly that b cubed divides a cubed plus.
Plus A squared C.
Yep, by definition of divide.
It's not that bad. You just substitute,
Substitute first, use part one first,
prove.
and then factor out whatever it is you're trying to factor out. You know,
You just gotta find it first. But I
you got to
mean,
find it first.
once you find it, then you can factor it out. And then once you factor
Yeah,
it out,
yeah, you got to have enough copies of B hanging around in each term to gather them together and get B cubed, right? Then we talk about why this other factor, not the B cubed,
uh-huh.
but that other factor
Yeah.
is actually an integer. And that's
And
when we use part two of the
okay.
definition.
And then once you find out once you do the nitty-gritty, then you basically get your proof.
Yeah, then you just basically we're just writing our wish because at this point we've got our wish. So we can just look at our wish and say, hey, what were we trying to do? Oh, yeah, we
Mhm.
were trying to show that a cubed plus a squared c equals b cubed times an integer m
Where and then we just say that it's an integer because we just did it.
because we did it.
We just did it. All right, that's
We
all
did
right.
it.
All right. I mean that's pretty good.
All right.
I get that. I just got to work on my factors.
Yes,
I work on my
factors are
factors.
important.
Factors are very important in when it comes to because basically that's how you get to your part two definition. So
Right. I'm going to give you a do later because this there's another way to complicate things. We can complicate things by having a kind of different relationship between the integers. Prove this true statement. And remember, in special homework 6, there was a bit of a complication because in special homework 6, um, it was A divides B, but it wasn't that A divides C, it was that B divides C. This is my
yeah, I see.
this is my grading key where I figure out exactly how many points everything is worth. Yeah. And so if some people lost 4 points because even though they wrote B divides C, when they
Mhm.
wrote the equations from the definition of divides, they accidentally wrote the equation as if the hypothesis was that A divides C. But the hypothesis is A divides B and B divides C. And that
Yeah.
makes things more interesting. So
Hmm.
let's do that here. For all integers A, B, and C with B not equal to 0 and C not equal to 0. So I'm going to be dividing by B and dividing by C.
Hmm.
If B divides A and C divides B, then C squared divides, let's see, A squared minus AB.
Well, in this now you're gonna give me a subtraction and put some
Yeah,
subtraction.
why not?
All right.
Because then, we'll have to use the fact that differences of integers are integers. Do you want to shall we just start it?
Yeah, we can start. We could do the first we could do part one and get the by the definition, and then after that I'll work it out.
All right, so you tell me what to assume.
We're assuming that B is not equal to a zero and C is not equal to zero.
Well, I'm going to teach you a little something about math etiquette. Before we start saying what B and C are not, it's really polite to let the reader know what the heck B and C actually are. So the
So
first thing
we're
we're
gonna
going
say
to do
that
is,
the element is
yeah,
Z.
we're going
We're
to
gonna say
say,
assume
assume B, C, and A, B, and C are integers.
A, B, and C are an element of Z in which where, or you say where
Where,
B.
you could say where, let's do that.
Uh,
That's nice, where. And now that we know what B and C are, it makes sense to say what they're not.
but they're not, yeah, for sure.
B is not 0 and C is not 0. All right, that's just sort of the kind of background setup.
Hmm.
What's the meat of our hypothesis?
We are wishing to show that.
Not ready to wish yet. We still haven't
Oh,
finished
we
that.
haven't even finished it yet. We haven't even finished it. Finish the
Got
whole
to
one.
finish that hypothesis. I know with all this other stuff, you
You,
think you're done, right?
yeah. We could go. Assume B divides A and C divides B.
Okay, B divides A and C divides B. And this is going to be a little different. We're going to have to think twice, about the definition of divides.
Mhm.
Okay, good. And then now what do we wish? Now I'm ready for a wish.
You are wishing to show that c squared divides a squared minus ab.
All right, I'm ready. All right. By the definition of divides, let's get our equations.
Minus AB. So first, by the definition of design, by the definition,
And I can write our definition up here. X divides Y if and only if Y is equal to
equals
X
y times
times K.
okay. So we can use yeah, we can use k here. You could say by the definition of divides, b divides a equals
Means it doesn't
means
equal anything because it's not a number. It's a statement.
statement. You're right. B divides a means a times b.
Careful. A is the Y.
Excuse me. So then it would be a equals. Excuse me. A equals
Good.
b times k.
Where K is an integer. Good. That's why I switched it up on us just to keep you on your toes. And what else do we have for hypothesis?
We have and c divides b means b equals c times an integer r, where r is an element of z.
Nice. Now let's dig into our wish so that we really know what we're shooting for. What does it mean to say c squared divides a squared minus ab?
Look back a little bit. We just did it. What does it mean? Oh yeah, we just did that. Hold on. Go to part two. Part two. That means we wish to show that. Can I say for this part? Can I say b divides a equals?
We're trying to just understand what we're really going to need to look at by unwinding this wish a little bit. You see, the x in our
X
wish
is
is
c
c
squared.
squared.
So
The
then I would just go
y
equal.
is
Yes.
the a squared minus ab.
So what I could just go a squared minus ab is gonna equal c squared times the integer m, where m is an element of z.
Exactly. And now what we really have is we've got this nice
Now
proof
we have
money to
basically
burn.
we have our coins,
Yeah, we
and now
do. Or yeah, I
our
should make like bitcoins.
yeah we have
And then we have our dreamy wish that is the work that we have to accomplish to get both parts of the definition of divide satisfied for these quantities. All right.
gotcha.
So, and this is really, really helpful because it tells us, oh, we got to look at a squared minus ab.
Yeah,
See what I
yeah.
mean? Because if you leave it like this and we read from left to right, it kind of looks like, well, we see c squared first. We might
Mhm.
think we need to be looking at c squared.
No,
But when
no.
we rewrite it like this, we realize, oh, we got to be looking at a squared minus ab and
Yeah, it's the
showing.
definition. Like
Yeah,
we rewrite the wish as if like by the definition, and then
exactly.
it makes it a lot more clear as to what we're trying to get to instead of just looking at it and not remembering the definition.
That's exactly right. All right. So, all right. So now what would we be cranking on?
Crank it out.
Yep.
B is gonna equal. Hold on, I gotta look. I gotta look.
Yeah. Just look at your wish.
Look at my wish.
That's why we bothered to write it.
Oh yes. Oh yeah. So B divides A. So it would be C. I have a question.
Yes.
If we're why do I focus on so we're wishing to show that c squared divides a squared minus ab. We figure out what a and b is. From there, wouldn't I write it? Couldn't I write it as bk squared minus bk times cr?
Yes.
Okay.
So when you say write it, let's tell the reader what it you're plugging into.
Yes, ma'am.
So what are you plugging into when you're doing that in your head? What are you really plugging these into?
I'm substituting our wish with the money.
All right, so let's tell the reader what side of the wish we're starting on. See, a squared, you're substituting into a squared minus ab, aren't you?
Yes.
That's why I'm saying tell the reader what you're doing.
Okay, yeah, you're right.
We're
You're right.
looking at a squared minus ab, and we're going to try to turn it into something that looks like this. Now, what did you say to do? I think you were right on the money. So, no pun intended. What do we do now? Substitution, right?
Substituting where a squared is going to equal bk squared
Quantity squared, good.
minus bk, and then we're making sure we put in the parentheses, and then we could go cr.
Yeah, or you could use a dot between them, but that's fine.
Yeah.
Now, let's see what we've got so far. We've got what? B squared k squared
Hmm.
minus BKCR. Do you agree?
Yep. And then let me keep
Well, we're
going.
trying to pull out a C squared. I don't see a C squared in here, and I don't see a C squared in here either. So what could we do to get some more C's?
Um, bk. Are we fact? Is this at the point where we were
Well,
factoring
yeah,
out?
but what do we need to factor out? We need to factor out a C squared. But we don't have a C
We don't
squared
have
to
a c-squared.
factor out. We got one copy of C in the second term, but we don't even see any C's at all, much less two of them
So
here in the
can we
first
factor out
term.
can we factor out k squared? Or can
No,
we choose? Can we choose whether between b squared or k squared?
no, this is where we have to go back and spend the money again. See, how do we see? We got a bunch of B's
Oh
here.
wait, hold on. Yeah, we have a whole bunch. I'm gonna say,
Yeah.
wait, hold on. We have a whole bunch of b's. Let's just substitute our money in.
Uh-huh.
Let's just use
Uh-huh.
our money.
Uh-huh. All right, now tell me what to write.
Um, you could put c r squared.
Yeah, CR quantity squared, and then don't forget our K squared is still there. Good. And then what can we do over in here?
Um, you could do c squared again. I mean, sorry. Use c r squared. Excuse me.
CR, is it being squared though?
So I have a question. Since we spent the money one time, can we spend it? Can we spend it?
Yeah, yeah, that's kind of the beauty of proof money. You can spend it as many times as you need
Oh,
to.
so
And that,
then,
isn't that beautiful?
so
So we have
then
put it just put in a CR for the B.
CR because there's not B squared. B's not squared right there, right? So then it'd just be CR and then K and then another CR. Yep.
Now let's see what we got. All right, what's CR quantity squared? What is that really?
C squared, R squared,
So we got C squared, R squared, K squared.
A squared.
Now
My,
over here, what do we got? Really?
we really got CR. Can you just go ahead CR squared?
It is CR squared, or we
Yeah.
could write it C squared.
C squared, R squared, just for monies, and then K.
Yeah. Now
And then
we're
now we could factor
seeing.
out or we could
Yes.
factor out and just take that thing out of there.
All right, show me. Tell me what to do. What's
Uh,
that thing? What's that thing?
we gotta use the distributive property and then we gotta factor out C
Yeah.
squared.
C squared.
We
All right,
put
what's left over when we pull C squared, factor out C squared from this first term?
we got R squared and then K squared.
Okay, good. R squared, K squared's left.
We ended there and
The
the parentheses. Oh
minus,
no, we're not ending the parentheses. Excuse me. Let me go
yeah,
correct that. Minus R squared K.
nice. Okay, now we are ready for part two.
And that is going to be our M.
That's going to be our M. So we got part one done.
Uh-huh. So this is our part one.
And now we're going to work on part two. Shall we just go ahead and finish it? It says do later.
Yeah, do later,
Forget
but
that. We're doing it
we're
now.
basically done. We're basically
I'll
done.
change it to now. All right, now how do we talk about this expression M?
You have to talk about products and differences
And yeah,
of
products and differences. And we're going to mention that
that
K and R are integers.
are integers. Yeah.
So since K is in Z, just go ahead and bring that down. And R is in Z. And what'd you say? Products and
And products
differences.
and differences of integers are integers.
Nice. What is it we're trying to actually say is an integer here?
We look back a little bit. I be forgetting.
Well, you can take a look here.
Oh, M is an element of Z.
Yeah, well, let's see. This doesn't really count as part of the proof by just writing the little M under here. We got to actually tell the
Make
reader
sure
what
that
M
we
is.
tell the reader what an M is. So it'd be M
Yes.
equals R squared, K squared minus R squared. K is an integer or an
Yep.
element of Z.
Yep. Now we got part two done. Now we've done it. And if we want to know how to wrap it up, look at your expanded wish and just basically we're just going to write this because we just did it.
Mm-hmm.
So a squared minus ab equals c
AB.
squared times m because we already told them what m was,
Mm-hmm.
where m is in z,
Yeah. Or M is an element of Z.
which means what?
Which means, can we go
Go back up to the first wish
with
to kind of
C
translate.
squared, which means C squared divides A squared minus AB by definition of divisibility.
Yeah, and WebAssign, they say definition of divisibility, don't they?
Yeah.
Instead of definition of divides. And there we have two nice little proofs of universal statements using definition of divides.
I basically did that one by myself. I'm not gonna lie, but that one is good. Like I'm starting to get it. I'm starting to get a lot more. A lot
Okay.
more. It was the not like I wouldn't like write it as monies. Like I gotta write it as if like what am I doing? Like what am I looking at and what am I substituting? That was my problem. I wasn't getting good at the substitution.
It helps to put the boxes around it and then you can check them off as you use them. And but sometimes you
Uh-huh.
got to go back and use them again, like you realized,
Yeah,
oh,
right
I got to go
here.
back and use the B again.
Yeah, because
Like
we
we
should.
used it once for that B. But then we don't have any C's yet. Yeah, well, we got one C, but we
Mhm.
don't have any C's here at all. So then we go back and use it again.
Double it
You
up,
just
right?
keep going back to substitute until you see enough of
You get
whatever it
enough
is
to
you're trying to
factor.
pull out. Yeah.
As
Yeah.
soon as I get that factor, then you could just go ahead and be like, oh, I got it.
You
And then
got
you
it. I
go
got
ahead and
enough of them.
you got enough of it. Yep. All right, that's good. All right, cool. I got that all written down. Like each one of these are a full page. It's
That's
crazy.
right. That's right. Each one of these are a full
I've
page.
I've gone through a whole notebook already. A
I,
not a comp.
I hear that so many times from students, semester over semester, year over year. They say, man, I'm working on my second notebook, or I'm working on my third notebook, depending upon how big the notebook is. So do you want a little sneaky preview of what we're going to do on day 14 tomorrow or Tuesday?
Yeah, yeah. Let
Want
me
a
get a
sneaky
preview.
preview?
Yeah, let me get a preview.
All right, sneak preview. Because we got just enough time for a sneak preview. Proof by contrapositive. It all hinges on this idea. Recall that if we have a statement, and like for all x, for all x in some domain D, that P of x implies Q of x. That's an if-then statement, right?
Hmm.
It's logically equivalent to its contrapositive. Like if this is the original, and we know it's an all statement because all the if-then statements are it all statements.
Hmm.
If we want to write the contrapositive, that's going to be a for all statement because it's an if-then statement
Yeah,
as
the
well. So,
contrapositive.
so it's still for all x and d. And if it was two variables, there'd be a y in some set f or whatever. Do you remember what the contrapositive of if p then q is?
If not Q, then not P.
Yeah. So if not q of x, then not p of x. So that's so the idea is this. Since a universal statement is logically equivalent to its contrapositive or its contraposition, when we prove the contrapositive, we are proving the original.
Hmm. Hmm.
In essence, proving the original. This is called proof by contrapositive. Why do we ever need to do this? Why would we ever want or need to do this? I'll give you some examples of some statements that are hard to prove directly, but easy to prove if we use the contrapositive and prove the contrapositive. I'll call this example, I'll give it a Roman numeral 1. For all integers x, if x squared is odd, then x is odd. We'll leave some room. And here's another one. For all a, b, and c and z, with c not equal to 0, if c squared does not divide a squared minus b squared, then C does not divide A, or C does not divide B. All right, let's look at the first one.
All right.
If we try to prove this directly, What would we assume?
400 x, we would assume that, hold on, let me reread. 400 is x if x is, so we would assume that x squared is odd.
Yeah, we would assume x squared is odd. And we would wish to show x is odd, right? Now, if what we know is that x squared is odd, by the definition of odd, we would get an equation that x squared equals 2k plus 1, where k is in z. Do you agree?
Yes, I agree.
But we're trying to prove something about x. We're trying to show that x looks like an odd number, that it has a certain kind of equation, right?
Yeah.
That it's equal to 2 times m plus 1.
Uh-huh.
So generally, when we have equations and we have an expression for x squared, but we want to solve and get an equation or an expression for x, what do we do? What is the algebra move that we generally would do?
We would factor out, when we factor out x squared.
Um, Actually, we generally would take the square root of both sides. You remember that?
Oh, I feel you.
That's the way that we would get this side on the left to be x, because when we take the square root of x squared, that's x.
Yeah, you're right. Yeah, you're right.
But then on the right, the problem with this is that we then have a square root, and that's
And
going to not help us prove that x looks
yeah,
like 2 times an integer plus 1,
yeah,
because we don't even know that that daggum thing's an integer at all, much
yeah.
less 2 times an integer plus 1. It's a square root.
Square root.
So that's a problem. However, if we wrote the contrapositive of this, what is the contrapositive of this?
Um, if for all integers x contrapositive, it would just be, let's say that p is x
It'd
squared.
still be for all integers x.
P,
This
so
is,
it'd be,
yeah, this is our P, this is
and
our
it's our
Q.
q. So as he said, so basically not q,
Yeah,
not q equals, so
so
the x, so then x is even,
yes, because
then
we know it's even or odd. So if
yeah,
it's not odd, then
then
it's
it has to
even.
be even. Then if x is even, then x squared is even.
And that's easy to prove,
That's easy to prove. Yeah,
right? I
because
mean, that's just super, super
yeah,
easy to
that's
prove.
basic.
And see, that's why proof by contrapositive is indispensable,
Yeah,
because it can prove something that's hard to try to, like, we don't want to deal with the square root. But if we prove if x is even, then x squared is even, we will have proven if x squared is odd, then x is odd. Same way with this. I mean, like, if we tried to prove this directly, our hypothesis would be something that says c squared doesn't divide a squared minus b squared. We get nothing from that. We get no equations if we know something does not divide something else. It just tells us there's a whole slew of equations we don't get.
Mhm.
Not helpful. But if we take this and write the contrapositive, let's write the contrapositive of this statement. It's still for all A, B, and C and Z with C not equal to 0. That's still
Yeah, that's never not gonna
that
change.
that still comes down because it's still a for all because it's a
Uh-huh.
contrapositive. All right, so now
So you would say, um,
we got to negate
that's our
this, right?
negate our cube. We'd say C divides A, and
Good job because that or switches
yeah, that
to an
orange, and so
and.
and C divides B, then C squared divides A squared minus B squared.
And that we know we can deal with.
You deal with, yeah, because we just spent time doing something like exactly like that. We just did that exact question.
Pretty much.
So I would just,
In fact,
I
we
would,
did one that was harder than this. This is
yeah,
easy,
yeah,
you
yeah.
know. In
But
fact, you could go ahead and practice with that one, you know.
nah, that's my do later.
Do later.
Do
That's
later.
the true later.
That's the true do later because we're about to do it in class on Tuesday. But but yeah, I see how that like, but because like, that's gonna be like it's gonna be super hard to try and even work with something like that. So you would basically just do the contrapositive. The contrapositive you've already worked on, so you should be able to do the contrapositive because it's basic. Or I mean, sometimes it may not be basic, but like it's something that like you're able to work with. It's gonna be a lot
Exactly.
easier to prove because we've already done it.
Because we get hypothesis equations we can work
We
with.
can work with, yeah, exactly.
You know, and we don't get stuck with crazy algebra that's impossible to deal with.
Yeah, it makes the algebra a lot easier. Just factorization rather than dealing with, because yeah, that doesn't make sense. I'm looking at the top equation, or like the top. It's like how are you supposed to get
That's
um
turning to an odd number, right?
exactly,
Yeah,
especially
good luck.
with the root, where you're gonna sit there for a while trying to do something like that. Like,
That's right.
all right, yeah,
So that's your sneak preview. And we will be spending this week learning proof methods that are not the direct proof method. Proof by contrapositive is one of them. The other one is called proof by contradiction, but we're out of time for tonight, and I don't want to put too much uh,
well,
preview out
you don't
there,
want to give me too
right?
much money.
One step at a time, you know.
Yeah,
But
okay.
both of these, you know, are definitely provable. And so this week we'll learn, you know, hey, if direct proof doesn't help us, can we use another method? And we'll find out that we can. And in fact, this week we're going to learn to prove that the square root of 2 is irrational. We're actually going to prove that this week, and you're going to understand every bit of it.
Of
Isn't
course,
that amazing?
yeah.
Because I mean, can you imagine that first week of class that if I'd said, please prove the square root of 2 is irrational?
I would have walked out.
Yeah, you've been in like your head would have exploded.
I would have dropped the class.
But by the time we are done with our day 15 lecture, you're going to follow that and you're going to be like, oh my gosh, it makes perfect sense. We'll use proof by contradiction.
Okay.
And I'll show y'all the logic behind that this
Wait,
week as well.
proof
Those
by
are our two
contradiction.
proof methods when direct proof doesn't help. It's proof by contrapositive, which is basically direct proof of the contrapositive,
Mm-hmm.
and then proof by contradiction, which is kind of a whole nother interesting ball of wax.
Wouldn't it be similar like proof by like proving the negation of something?
Ah, we definitely, you know what? You're really close. We we can't prove the negation of a statement that's true because if a statement is true, its negation is actually false.
Okay.
But what we do is we assume the negation is true and we show that leads to something impossible, like it leads to 0 equals 1, or it leads to a number is both even and odd, or
So
it leads to a number is rational and it's irrational. And then we say, gosh, assuming the negation led to something that's impossible, that's called a contradiction, something that
okay.
can never happen. So the negation must be false, and that means the original actually must be what's true.
Okay, makes sense. So the contradiction. So for example, if the contradiction, I'm getting a little bit too deep into it, but because think about like the x squared equals 2k plus 1, where k is an element of z, and then we go ahead and square root that, that would be a contradiction to where like the original has to be true. Oh, I don't know if I'm on anything right now, but like the original
Not
has to be.
quite. Not, you know what? There is a way to actually prove x is odd if x squared is odd
Uh-huh.
directly. But it's requires what we call a big gun. We can never prove the negation of a true statement is true because the true statement cannot be true at the same time that
All right.
its negation is
So
true.
location is
But
true.
what we can do is we can assume the negation is true, show that that leads to something impossible, and then say, well, that means the negation never could have been true in the first place. So the original must be what is true.
All right. All right.
All right.
A lot
Well,
of money. Of
thanks for playing and thanks for being here so that it made a video for other people to enjoy.
course, I'll be here Wednesday.
All right.
All right.
If we're gonna have a Wednesday pop-up office hour, I need somebody to email me and ask for it.
All right. I'll email you
All
probably.
right.
Email you.
Hey, make me earn my keep. Get your money's worth.
Get my money's worth. All
Get
right.
your money's worth. You paid for it.
Paid for it.
All right.
All right,
I'll see you
Professor.
later, man.
Of course.
Good night.